Alright, so welcome to the first video on ratios in polygons. So I don't really know, I don't have a plan. We're just going to look at some math. I'm going to review some basic algebra and hopefully give you some insight into some geometry. So maybe first thing we need to talk about is what we mean by a polygon. So if we look at our triangle, which is the simplest such polygon, you have vertices and edges, right? Pretty straightforward, right? So these are your vertices and those are your edges. So you have this collection of edges and vertices. And in particular here, we're going to be looking at regular polygons for now anyway. So regular just means that all the edges have equal length and all of the interior angles are equal. And the Triangle Sum Theorem which is dependent on the parallel postulate of Euclid, which I'll talk about. So postulate 5. So the Triangle Sum Theorem says that in Euclidean geometry, there are non-Euclidean geometries. The sum of all of the angles in a triangle is 180 degrees or pi radians. And their interior angles, at some point we'll get to what we mean by an exterior angle, but these are the interior angles. So the sum of the interior angles of a triangle, any triangle, not just a regular triangle. So sum is always 180 degrees or pi radians, and radians is like a non-unit, so we don't have to write the units there. So if all of our interior angles are equal and they all sum to 180 degrees or pi radians, that means that each one of these three angles in our triangle is equal to 60 degrees or pi over 3 radians. So all three of those angles are equal. And radians and degrees both have, their pros and cons. I like to work with fractions generally, so radians are really nice, especially the fact that they don't have a unit associated with them. But often we're kind of conditioned to use degrees, so I also default to that a lot. So anyway, I'll try to mention both degree and radian measures for any angles that we talk about. All right, so this equilateral triangle, all the side lengths are equal, so they all say have edge length x. And equilateral triangle is pretty simple. There's not a whole lot going on here, but there are some things that we can measure. So oftentimes when you're constructing geometry, we want to know things like what is the length of a diagonal, what is the length of a radius, what is the length of an apothem. And so every polygon has a center, and if we draw a segment from the center to a vertex, we call that a radius of the polygon. Right, so that's a segment drawn from the center to a vertex. And we can also draw this thing, which we call an apothem. And this is a segment drawn from the center to the midpoint of a side. And these two measurements are important. The radius also happens to be, this terrible picture, but it also happens to be the radius of a circle circumscribed about the triangle. And the apothem is the radius of the circle inscribed inside the triangle. Okay, so how would we find these measurements in our equilateral triangle? Well, so the first thing we're going to look at here, before we look specifically at our radius and our apothem, is I want to look at the altitude of our equilateral triangle. And so what we mean by altitude, and all of these variables that I'm using are A, H. I could be using any variables here, okay? Just, commonly R for radius, A for apothem, H for height. So that's why I'm using those, but they could be any variables. So altitude, and when we say altitude, we mean a segment that is perpendicular, how do I want to say this, drawn from a vertex perpendicular to the opposite side. And so even if I have a triangle that's not an equilateral triangle, say I have something like this. So here, if I wanted to draw a segment perpendicular to the side opposite that vertex, I would have to draw it outside the triangle, and so that would be my altitude. So when I say opposite side, every triangle has 3 sides, and so these two I would call adjacent to that vertex, and I would call this one opposite. Right, and if we start labeling our triangle to name like our angles and our sides, generally the convention is that you use capital letters to name your vertices and lowercase letters to name your sides, and the letters would correspond with an angle and its opposite side. Okay, so what do we remember about our equilateral triangle, right? Is that all three sides are the same. And since this is an equilateral triangle, when I draw this altitude, it's going to go exactly to the midpoint of this opposite side. So that means that this measurement is x over 2. So what I want to do is I want to find the length of this altitude in terms of my edge length x. So to find altitude h in terms of edge or side length x. What we're going to do is we're going to use the Pythagorean Theorem. And I'm sure most people remember this, but if not, I'm going to go over it. So Pythagorean Theorem says that if you have a right triangle, so it only works if you have a triangle with a 90-degree or pi over 2 angle. So it has to be a right triangle. So in a right triangle with legs of lengths A and B and hypotenuse, so hypotenuse being the side opposite the right angle, of length C, then the equation a squared plus b squared equals c squared is true. And there are a lot of interesting proofs for this. I'm not going to prove this. You can look that up. But basically, if you were to draw a square on each of these sides, the area of this one would be a squared, the area of this one would be b squared, the area of this one would be c squared, and if you were to add those areas up, they would hold in this relationship. Okay, so we have this triangle here, and I'm going to redraw half of it. So right now I only need this right triangle that's half of my equilateral triangle with hypotenuse x, short side x over 2, and altitude h. And remember that each of the angles in my equilateral triangle were 60 degrees, or pi over 3. And so when I draw that altitude, I'm dividing that top angle in half. So this is our 30, 60, 90 right triangle. Sometimes they just call it 30-60 since it's implied that it's a right triangle by having a 90-degree angle. And then if we want to think in terms of radians, pi over 6, pi over 3, pi over 2. Okay, so let's set up our Pythagorean theorem. So my two legs have length h and x over 2. So I'm going to say h squared plus x over 2 squared equals x squared. I'm putting parentheses around the x over 2 so that I can make sure I'm squaring the entire thing. And so if I square that, I don't know, I wrote equals. I get x squared over 4. So if I square a fraction, or I raise some fraction to an exponent, the rule is that I raise both parts to that same exponent. And the same thing would apply if I were multiplying two numbers inside an exponent. I would raise both of them, but it doesn't apply if you're adding or subtracting. That's like a really, really big no-no. P. So Cool if you're multiplying and dividing, not so cool if you're adding or subtracting. And the reason it works for multiplication and division is because exponentiation is really just repeated multiplication, and division is really just multiplying by a reciprocal. And so you have commutativity and associativity of multiplication. So the order you do things there doesn't matter. Okay, so now I'm trying to write h in terms of x. If I'm trying to solve for a variable, I want to get that variable by itself. So first I want to isolate my term with the h. And so what I'm going to do, I'm not going to skip steps since it's the algebra a lot of you guys want to see. So what I'm going to do is I'm going to use the subtraction property of equality that says if I have an equation, that equation is still true if I subtract the same thing on both sides of the equation. So what I used there is the subtraction property of equality. Cool. So if I have something and I subtract itself, they're going to cancel. Any number minus itself is 0. So on the left-hand side, I'm left with h squared. And on the right-hand side, I still have this x squared minus x squared over 4. So in order to subtract those, I need to get a common denominator. Well, I can always think of something that's not a fraction as being over 1. And here my common denominator would be 4. So in order to get that here, I'm going to multiply x squared by 4 over 4. And the reason I'm allowed to do that is because 1 is the multiplicative identity. And so basically that just means I can multiply any number by 1 and it remains unchanged. And I can write the number 1 as any number other than 0 over itself. And so I can multiply by 4 over 4, 5 over 5, x plus 7 over x plus 7, as long as I'm being mindful of the fact that I don't have 0 in a denominator, because that's when things get all crazy. Okay, so now I have h squared equals, and to multiply fractions, we multiply across, and I'm going to write that as 4x squared over 4 minus x squared over 4. Now I can subtract, and so to subtract fractions, I just subtract my numerators, so a minus b over c. And so I have 4x squareds minus 1x squared. That gives me 3x squareds over 4. All right, so then our last step is to get rid of that square. Well, generally speaking, to undo a function, we want to apply the inverse of that function. Now, there's this whole technical thing where in order to have an inverse, the function has to be 1-to-1, and the square function is not 1-to-1, so you have to restrict the domain in order to define its inverse. But in our case, because we're talking about lengths, we're only dealing with positive values, and so we don't have to worry about negative numbers. Usually, if I were solving this equation, so the inverse of the squaring function is the square root function. And so normally, if I were to take the square root of both sides, what would happen is that I would have to take into account that this guy is actually the absolute value of h, which I know sounds really crazy. I'm getting into some really technical stuff right now, but whatever, algebra. And the reason for this is because when we take a square root of a number, we're talking about the principal square root. So if I want the square root of 4, I want just the number positive 2, not the number negative 2, even though both 2 and negative 2, when I square them, give me 4. So when I take the square root of h squared, I want to be able to get the absolute value. Well, so then to get rid of the absolute value, and this is where it, this is what you might be used to seeing, is just to go from this step to this step, is that this is either going to be plus or minus this square root, depending on certain conditions. So the idea, so the couple of rules that I used here, if I have the nth root of x to the n, that's going to be equal to x as long as n is odd. So if I take a cube root of 8, positive 8, that's going to be 2. A cube root of negative 8 is always going to be negative 2. And then it gets problematic when I'm trying to take even roots. So, and then we use the rule that the absolute value of x is equal to x as long as x is greater than or equal to 0, and it's equal to negative x if x is negative. And that may seem kind of strange, but if I take the absolute value of negative 2, that's equal to positive 2, which is the negative of the negative 2. So the idea there is just that we're trying to write things in a positive way without using absolute value. Okay, so then for our purposes, again, since h and x are always going to be positive, they're not even greater than or equal to 0, because if either one of them were equal to 0, we wouldn't have a triangle. So since those are always positive, I'm going to say h is just equal to the positive square root of 3x squared over 4. And then what we can do is, since all this stuff inside is multiplied and divided, is I can break it up. So that's the square root of 3, square root of x squared, square root of 4. So nth root of x times y, we'll say, or let's even do xy over z. That's equal to the nth root of x times the nth root of y over the nth root of z. So if I say the nth root of x, that's the same thing as saying x to the 1 over n. So all of those exponent rules hold for radicals. Okay, so then again, normally I would simplify the square root of x squared as absolute value of x, but since we know x is positive, I don't have to worry about that. So I'm looking at the square root of 3 times x, and the square root of 4 is positive 2. So we get that our altitude is root 3 over 2 times x. Cool. So that means that in my equilateral triangle, that I have side length x and altitude root 3 over 2 times x. Awesome. All right, so now what we said we wanted was our radius length and our apothem length, right? So I'm going to draw my circle in here, and hopefully you would agree that if I draw all of my diagonals and all of my apothems, these 3 things are radii, these 3 things are apothems, right? So we can set up some equations here. Now, couple of things that I want you to notice, and this is really cool. So what I've done at the center here is I've set up 6 radial divisions of a circle. So all the way around is 360 degrees, or 2 pi. And if I divide by 6, I get either 60 degrees or pi over 3. So each of these guys is 60 degrees or pi over 3. And, well, at my vertices, I know that those are still equal. And so this little triangle here, made up of my radius and my apothem and half my edge length, is still a 30, 60, 90 triangle. And so cool thing is that similar triangles that have the exact same angle measures have proportional side lengths. So similar triangles have proportional side lengths. And typically the way I teach my students to memorize the 30, 60, 90 triangle. Actually, let me draw it a little bit more accurately. So typically, I just have them measure or memorize a special case. So if we look at our big one with hypotenuse x, so let me redraw this over here. So there's my 30. There's my 60, there's my 90. So I have hypotenuse x, side opposite the 30, x over 2, and side opposite the 60, root 3 over 2x. As usually, I'll just have them memorize the case where my shortest side is 1, my hypotenuse is 2, which is consistent with x and x over 2, and the side opposite the 60 is just root 3 times the shortest side, so the 1, 2, root 3 case. And I think that's pretty simple to memorize. So the idea here is that I can always get from one side to another by a scaling factor, either multiplying or dividing. So it just depends on, which measurement we're given, which measurement we want to write this in terms of. But let's say we're trying to write everything in terms of x. So that would mean then, well, if my side opposite my 60 is x over 2, I get to the side opposite the 30 by taking that root 3 and dividing by root 3. So that means that my apothem is going to be equal to x over 2 divided by root 3. And dividing by a fraction is the same as multiplying by its reciprocal. So we could think of this as x over 2 times root 3, which is perfectly acceptable. Or we could rationalize that by multiplying by root 3 over root 3, which would give us x root 3. Root 3 times root 3 is just 3. So it would be x root 3 over 6, which is, totally fine too. So we can say that if our side length is x, then our apothem length is x times root 3 over 6. And then we get our radius by multiplying that side opposite the 30 by 2. So in this case, the radius is twice the apothem. and that's pretty cool. So, and that's only going to be true in this equilateral triangle. So 2 times x root 3 over 6. Let's see, how do I want to explain this? So 2 is the same as 2 over 1, and maybe I'll actually leave this as x root 3 over 2 times 3, right? That was one of the ways we had that written. And I mentioned before that multiplication is commutative, so I can multiply this in any order that I want to, and I don't need the 1. And 2 over 2 is 1. Oops, not root 3, just 3. And so this is equal to x times root 3 over 3. So my radius length is x times root 3 over 3. Now, if you're doing ruler and compass geometry, you may find that rather than writing your apothem and radius in terms of your side length, that maybe you want to write your side length and your apothem length in terms of your radius. So let's just kind of look just very briefly at how some of these things are related, right? So we said the radius is equal to twice the apothem. So that means if I divide both sides by 2, that my apothem length is equal to my radius over 2. And then my side length, let's see, where do I want to write this? So since my radius is equal to, and I'm going to unrationalize this, which is going to sound really silly because you grow up with your teachers always telling you to rationalize things, but I'm going to unrationalize it. I wouldn't normally show that work. I just know that it's x over root 3. So if I know that my radius is x over root 3, then I can multiply both sides by root 3. And so I can see that my edge length is equal to my radius times root 3. And so in our equilateral triangle, maybe you know your starting radius, and so that'll help you find your edge length. So let's say, you're starting with a circle, as we do in ruler and compass geometry. You set your radius, and now you know what your edge length and your apothem are.